Okay, cool. Good morning, everyone. My name is Natu Lauchande, and I work as a principal data engineer at a company called UniWs in Cape Town. I work in the machine learning engineering department. And on my presentation, I'll be talking around like a journey that I've gone with my team on trying to extract and understand like how machine learning engineering, machine learning systems were created across the industry. And yeah, and I'll be talking about a couple of tools and like different principles that we kind of extracted from the research that I've done. And I'll show some examples of some toy implementations, and I can actually like further on talk about like uh, real world implementations and questions. So this is basically the like let's say the TLDR of my talk, and it's basically cool. So move on. So going to the agenda specifically. So what is in scope for this presentation? So basically, like I'll be outlining a set of machine learning engineering pain points in industry, and I'll try to explain like in simple terms, in a way that even if you don't have a machine learning background, you can relate with these pain points. And these are the main pain points that we found like on our context. So like just to give a bit more context, so I work for a fintech company, and like you mentioned in finance, like there are a couple of relevant applications of machine learning, for instance, like fraud detection or credit risk and or churn detection and things like that. So I'll just explain like some pain points that are very common and we also found while implementing different systems. And also like the second step is that like we went out to the world and tried to understand how the world actually set it up and create these architectures. And like we spent some time studying like the main architectures for some of the big tech companies and a couple of open source tools. We're gonna go through a couple of these tools and like and expose you guys obviously to the tools. And then like I'll outline a couple of principles that we found, but assume that these principles are not complete and they are basically like our findings of this problem. And I'll also give you like a walk through some examples of like of using a couple of tools. One of the tools that I'll talk about is MLFlow. Another tool is SageMaker. So what is out of scope on this presentation is a detailed review of ML systems. So don't expect this to be like super rigorous. Any specific data science algorithm solution. This is not the science talk, and tutorial on any tool. So it's basically a overview of pain points, talking about architectures, outlining some principles, and showing some examples. And then I'll be keen to get some questions from you guys on chat. Cool. So setting this head in context, so machine learning today is really easily accessible. Like anyone can go and take a course on Coursera, Udacity, Udemy. And like in some ways, like you can, like after finishing a course, like because the tools are easily accessible today, the abstractions, some of them are quite good actually. So you can assume that like, machine learning and you know how to like solve world's problems with machine learning. Like the big problem, uh, like working on a Jupyter notebook might be straightforward, but when you want to actually scale the solution or provide like a repeatable way to run the solutions to your company, it just generally becomes problematic. So the set of tools and principles that I will outline here are like, how do you move to the next phase? Now you know machine learning. Like what are the barriers to you to achieve the next phase on scaling? So going specific to pain points is like one of the most important pain points is actually getting your models from dev to production. As I said, like it might work well in your development environment, even if your development environment is your own machine. Yeah. And then like obviously when you try to just like deploy the system, and you might have a situation where like it's just impossible to run. Like even if you like, I've seen examples of people trying to transform Jupyter notebooks into applications, like, and they were really believing that this was like a reliable, possible reliable solution. So, and this is actually super problematic. And like, yeah, it's easy to get it working in dev, and it's easy also to outsource this as a problem for the operations. So another big problem on machine learning systems is actually data pipeline entanglement. A lot of these machine learning systems do depend on a lot of data sets and a lot of transformations. So like the industry, like is still mature, the tools are still maturing, the principles are still being spread. And let's say, like in all fairness, like you don't learn in a university or in a school how to do machine learning engineering. And most of these things like really need to do in practice, and particularly like the component of data engineering, like the critical piece of machine learning, as you guys know, is getting the data right. This data generally needs to be enriched, needs to be transformed, and in order to like actually allow the machine learning systems to infer value of the data for scoring and inference. Cool. Another big pain point, but this was mainly from like interactions within my team and like data scientists, was like a simple way to run experimentation, to manage experiments. So you basically want to find like the best model, and like how do you go through this? Like how do you ensure that like only like a subset of your population goes into a specific experiment? How do you run like multiple experiments at the same time? So this is, and how do you track more than anything? Like, because these things like are not trivial, and the tooling that's available is actually not trivial. And if it's available, sometimes it's extremely expensive, and it doesn't even fit the bill of the normal requirements. So these are some of the big issues. Yeah, on all this like survey of big pain points that I've gone through with my team. The other point is just specific to machine learning, is where when your metrics in machine learning are actually not like model is not, the performance of your model is not the one expected. You can either be underfitting or overfitting. Can explain this a bit. Underfitting is when your model doesn't work as expected, but you really need metrics and visibility to say these things. Or overfitting, or when your model just like in some way memorizes the training set and it's unable to generalize. So like, but this is just to expose the need for metrics in machine learning systems. So you need to have a simple way to manage metrics and view machine learning metrics as well, both in production, in development, and in training as well. The other point is actually data. So let's say real world data is super dangerous for some of the models. Like, because most of the times the models are created with the subset of the data, and that might not be represented. Real world data actually might have a lot of issues on it if you don't actually properly prepare the data or sanitize the data. So I would say this is like one of, alongside data pipelines and data quality is another important issue on machine learning, because without data, like you actually can't make these inferences or create scoring systems that are able to actually add value to the business. So real world data is like let's say the old data space. We need like a better narrative or story, like in a simple narrative to address this problem in the machine learning world. Yeah. So yeah, how do you crack these issues in production, and how do you ensure that you have like actually like a chance through these problems? So there's this new area, like new in some sense, called machine learning engineering, and technically, this area like allows you to like delve into some of these problems that are not like the core of like a research scientist, of a machine learning scientist. You can start building like engineering solutions to these problems that like are not completely new. Like data was a problem before machine learning being like a buzzword that is at this moment. So development, like the difference between development and production, like is the problem of the software engineering world. And like it's kind of like solved in some way with containerization and things like that. But let's say machine learning engineering is trying to create scalable and deployable solutions to these different problems on the machine learning space, and these problems are basically represented by the pain points that I described before. Cool. So just delving a bit more on this, on the context of machine learning, what is machine learning engineering? There are multiple definitions in the industry. Like in some companies, machine learning engineers are model creators. In other companies, look like a lot like DevOps operators and SysDev team members. But in general, like one accepted definition is just like a mix-up of skills. Let's say you have a mix-up of like data science skills. You understand the models, understand what is model performance, and you can actually like optimize the runtime of models if needs be. And you can find the right like hardware abstraction to run your models more efficiently. And you also have data engineering skills. When I speak about data engineering, I'm talking about wrangling data, like complex data architectures with data intensive systems, and you know how like let's say database low latency databases work, how feature stores work, and things like that. So there's like the hard component of like hardcore data systems in here, and obviously you know how to deploy, how to make your like how to create your CI/CD pipelines for the same systems, and obviously like the very basic principles of backend engineering, making sure that like you have APIs and that are scalable, horizontal scalable depending on your problem, or you're using event-based systems. But like in the end of the day, most of the times your machine learning system is represented as a microservice in like with a client. So this is like to bring up the context and set the scene of what is this machine learning engineering. That's, for instance, like the title of this talk. So now I'll go to a couple, like explaining a couple of architectures of like relevant architectures, like machine learning engineering architectures, and like and from this like we'll extract some principles and we'll talk through them. So one of yeah. Oh, so is this? So yeah, so this is like more or less the workflow of machine learning project as defined. And I think this was a article by Uber. So basically, it looks like in some way a standard like software engineering project, but there's like a bit of nuances here. So for instance, like you obviously need the business component, like defining the problem, understanding what is the business that you're trying to solve, and you prototype. So this is where like the data scientists are like this is the area where the data scientists will make all the difference, because they can even run on the machines, and sometimes they can require obviously engineers to help do things like that. So this is like most likely the prototype would happen in your own machine, or you might have access to ad hoc instances or machines. And on the left, we start getting into the realm of machine learning engineering, where you start making when you start to productionize your solution, the way you productionize your models, the deployment of your models, how you make predictions, how do you make these predictions available, how do you monitor your predictions, and obviously like the insights component is like I think teamwork. So this is kind of an idealized workflow. In real life, it really doesn't work like that, because like it really depends on the company. Sometimes it's just one person doing everything, and sometimes there's even no one doing business needs, and like people just move into the solution mode. But this is like what kind of like we expect from a machine learning normal machine learning project. Cool. Again, on the machine learning engineering contextualization. So you have data engineers that are responsible for although like they really like on the left they have a very small square, this is actually like one of the critical components of this process is getting the label data and getting the data and transforming the data and augmenting the data. This is like extremely intense. And obviously, data scientists that provide a piece of training code, can be in Python most likely, and like spend their time on model build. And the output is actually a model. Like it might be seen sometimes binarized, and there are a couple of models in flavors like sklearn and TensorFlow and things like that. And machine learning and developers are responsible for the rest, for deployment and making sure that this is in production. This is kind of like ideal. You can have one person doing everything as well. Cool. So another important piece of like information is like to give context on those different components that you might need in a machine learning system. This is fantastic paper by a team at Google, led by Scully and I don't remember the rest of the people, but it's just like a very like seminal paper on the area. So like this is like the description of different components that you have in a machine learning system. So you have monitoring. Monitoring is like looking at your predictions and trying to verify how your predictions are running. You have a serving infrastructure, basically like the thing that like makes your API work. You have to manage machines and the resources in some way, like talking Kubernetes or like any other tool. You might have like analysis tools to look at the results of your machine learning system. You can have obviously process management tools like low-level tools, just like verify and manage memory and things like that, or supervisor, for instance. You need data verification. You need to ensure that the data is correct. Obviously, you need data collection as well, and you might need to configure. Imagine if you're running like a shop for fraud models. A lot of these models need to be localized. Depends on on how a specific region acts on like a specific situation. For instance, like for things like consumer behavior, these models are super localized. You generally can't use a model from one country into another country. So like you need to have some form of configuration in order to ensure that you can run all these models. So a couple of principles that we kind of figured out with time, and also by what we have seen so far, is like you need kind of a software engineering approach, a platform view of your ML functioning. You need an integrated, reliable data lifecycle, and obviously we know that data is extremely important. Like the data lifecycle needs to be reliable, and we need also a reproducible and reliable model management. So your model needs to be taken like as a piece of software. It needs to be managed properly. And you need to make sure that your data scientists are fast. So these are kind of like the kind of principles that guide a lot of like the research on this talk, and the different tools that you will see lots of tools. And please, this is just like a survey. Feel free to go and explore a bit more like on your own time. Like there's no intention of being a specialist on any of these tools. So one important system that is like kind of a reference system in the machine learning engineering area is Michelangelo. So even if you're planning to do your system, I'll recommend always taking a look at how the system is architected, and I'll just describe. So this is like the Uber main machine learning platform. So in order to scale machine learning and making machine learning accessible to everyone, in order to be able to innovate fast, they have decided to create a platform called Michelangelo to accelerate the deployment of machine learning systems. And how does this system works? First, there are two concepts. We have the online world and the offline world. So model training happens offline, and you can also have predictions happening offline. And for real-time things, like I would imagine, for instance, on Uber, predicting the duration of a trip. Like this is kind of something that needs to happen in kind of like a real time, and you generally will need to mix up with data that comes in real time. So the location of the place where you are asking, and potentially temperature or potential traffic information, that you of the place where you are is important to make the decision of how much time you take from get to point A to B. So and I'll just try to describe each of these boxes in a high level. So you have the get data component. This is like data management, getting data, data preparation, and I'll talk a bit about feature store just now. And you need a component to train your models, like get the data structured and train the models. And you need a way to manage and evaluate your models. So we're in particular on this incantation of Michelangelo used a famous non-relational database called Cassandra. And you have like the infrastructure to deploy, predict, and monitor your systems. So they here have two approaches. So for real time, obviously this is most likely a REST API backend, and for let's say for batch systems, you use Spark, and they also monitor performance of the predictions, like with Spark as well. Like they retrieve the data from the train from here and a sample of the data, and they can just like monitor multiple things. And this is like traditional data warehousing, data lake. So they use Spark for it, and they have this important concept of feature store. So a lot of these features are reusable. For instance, let's imagine a distance to city center. So multiple models might use this feature, and it's good to share between data scientists, so you don't repeat this the feature definition. So this is like why these feature stores are here. So they are basically a place to put like to abstract all the data manipulation into like a simple feature store that's feed into the model. So this is kind of like one of the like world reference architectures, and a lot of the systems that I see in the industry are very similar. We'll go through a lot to some more that are not like just to get you guys like exposure to others or to other architectures. So this is PIML. So it's still like a system that is on still on it's Michelangelo. So this is like another approach to deploy models. So basically, from from the data scientist context, you can send your model straight to a Docker registry, and it's productionized. So the original versions of Michelangelo, they required the engineers to redo the models that the data scientists created, and like a lot of engineers had to recreate this in Scala and Java. So with PIML is basically a way to, from Jupyter and Python, just pushing these models into the prediction infrastructure automatically. And this is like the tendency of the last generation of tools. And this is a bit more like on the feature store. So basically, these features are like this feature store contains the information from from the online store, like the store that's serving, and the store that is training. So it's a place where you can join features, use features, and also specify features. Facebook has a similar platform. So like what I want to convey here is that a lot of these companies are thinking on machine learning as a platform in order to accelerate and reduce like let's say the cost of investment on this machine. So things are centralized, and it's easy to actually innovate in these tools. So Airbnb also has a system called Big Head. Let's say it's similar in spirit, but like obviously the details are super like are a bit different. So there is this concept of feature store here that we find in Michelangelo. There is some kind of automation. So this is like mostly for batch processes. There is this concept of a service as well. And there is this concept of like model registry potentially, like sorry, model repo. So they use Git here, while on the Michelangelo case they used Cassandra. And obviously they have like this looks like a Kubernetes cluster, but a Docker service that like derives that serves the models. So at a high level, the systems in Spirit are super like similar. They have similar components. So we also like looked at those different services like from like cloud providers as well, and we compared with like what. So this is based on a slide by I think it's yeah, Microsoft, I guess. So this is just like a comparison of different cloud providers and the built-in tools. So generally what we can see is that these built-in tools from like companies are generally more like very beefed up in terms of data management, because this is where like a lot of the like critical work and the IP is also in. And this is generally neglected in a lot of the tools. And let's say if you want to like in a couple of tools that I'll be talking about as well on the next slides. One is MLFlow. It can help you in a couple of things like training, experiment training, and yeah, model management is pretty good, and also some serving as well. So if you want to play around with one of these tools and look at how they look like, MLFlow is a good candidate. And there's also Kubeflow, it's a bit more complete. So they just moved to version 1.0 recently, and it's a project that's moving very fast as well. So one of the concepts like that is making waves on the machine learning world is this concept of continuous deployment for machine learning. So basically everything, so this is like a pipeline, imagine a CI/CD pipeline, and it can actually be started by many teams. So, or like interact by many things. One is training code. Like if your training code changes, obviously your CI/CD pipeline starts, and you can have like candidate models out of this, and you go to a phase where you model evaluate, you try model A and model B, and obviously like experimentation, and you take metrics and you decide what is the best, for instance. Then you productionize your model, but this is all in a CI/CD system. Like it will be on SageMaker or like in let's say in whatever is the version of the system. So your productionized model goes into a testing phase where it's tested like around like canonical predictions, and then from there like your model like goes as an output and deployment, and is deployed on for instance in production. Went very fast here, but the concept here is that so everything is part of your continuous delivery pipeline. So if you change data, training data, your continuous deployment pipeline will be triggered. If you change training code, your continuous deployment will be triggered as well. And you have this system like running in CI/CD, doing training, refuting for you. That's pretty interesting concept. So I'll just like the brief on a couple of tools for if you want to use for data management, and we noticed that there's a gap in some of the cloud providers. So there's this Apache Delta Lake tool for that is by Databricks. So it allows you to version data and have checkpoints, and also like to be able to time travel like with data. So it's very good to also like recreate like a model and point in time and draw back if there are problems. Another cool tool is DVC. Does kind of like treats your data as code and integrates very well with Git and potentially with your storage. For instance, like Git and S3 are a famous combination. So you have just a link to your data in S3. So these tools are the tools that are like can bring your, let's say, your machine learning engineering practicing to the next stage, because they are handling the most important like asset on this machine learning pipeline. That's data. Cool. From a quality perspective, I've played and I've used two tools that might be interesting. So if you're using Spark, there's a tool called DQ by Amazon. So it's an open source package. So basically, it allows you to create constraints of your data and verifies the constraints, and they can run in Spark. So it can also do something very interesting. So you can provide a data set with quality, and it can actually do constraint suggestions, and you can then use the suggestions to ensure that your data always meets the specification. And obviously you can have a data quality report, and then you can use the metrics that are produced, and you can even integrate this in your CI/CD pipeline or CD for ML. So this is an example of another tool in Python that is a bit similar. So to data lifecycle to DQ in some way. So you can like have this very interesting like this is a pandas data frame, and you expect column values to match a regular expression, for instance. And this is the report that the tool provides to you. So there are lots of interesting things around distributions of the data that you can use actually in production to get like interesting data quality information. From a feature management perspective, so there is another tool that's being in the process of being integrated in Kubeflow called called Feast by a South Asia company called Gojek. But like it should be like better. This was like kind of 6 months ago. So in some way, in high level, they try to implement this concept of feature store. So if you're thinking of a feature store, this is a good tool or architecture to be inspired on. So if you remember Michelangelo, so this like in the data ingestion process, they kind of have this concept. So like there's a batch feature data, streaming feature data, and you have this concept of like communicating between these two worlds, and you have a serving API for your data, and you have like a warehouse store for your offline models. And obviously there's a core API, so you can create data sets. You can register features. Features are like first-class citizens here. You can actually trigger ingestion. So one ML engineer or data scientist can discover features, train, and deploy models. And basically the interesting thing is that like you can abstract calling a feature, for instance, by name. Let's say I would say distance to the capital, for instance. It's like distance of the current user to the capital. This is like quite an evolving like a feature to implement. But with this kind of tools, you can abstract. So for instance, everyone, all the data scientists in your company, or in some way analysts as well, can have access to it in your company. So this is MLFlow. So I'll just like walk through like no time for demos. So what MLFlow allows you to do is experimentation management. So you have a UI to manage and log different models. You can have reproducibility. You can run your models straight away from GitHub, and you can standardize ML projects. And this is just generally a problem. Like, so they have like kind of like a package format for machine learning problems. And you can actually standardize deployment operations. So you can deploy into multiple run times. So you stop being like constrained to one specific provider. So you can run on Kubernetes, Google Cloud, Azure, and SageMaker. So there is the tracking component. So it basically records and query experiments, code, data, and configuration results. So you make a change, this change is always available, and you can just like attach this to your results. So there's a very nice and neat package format that you can use and reproduce in any of the execution engines. And also they have a specific model like format that allows you to deploy in SageMaker at the same time, Kubeflow, or like in your local and things like that. So I'll go through a simple form. So the model format, like one of the important concepts is flavor. So you can have like, let's say TensorFlow flavor or sklearn flavor or PyTorch flavor now. You can decide where you want to deploy this flavor of models, either in Docker or in Spark or in one of the cloud providers. That's super neat. It's a super neat abstraction, in my opinion. But it doesn't fit all the bills, like for very specific models where there's like a lot of, like it's a bit more complicated than what it looks like. But like if you have a standard problem and it fits the bill, like it's a very interesting tool to look at. So this is like a pipeline, and like and look at the role of MLFlow. So let's say when you're doing model deployment and scoring, or model development as well, So you can use the MLflow registry and the MLflow the metrics component and artifacts to store your data. So you deploy a model with MLflow, and during scoring, you can also like send the metrics that you're receiving to MLflow if you want. Cool. And obviously on the modeling pipeline as well is the most important component. And this is an example of an interesting like architecture. So I'll go quickly to one example that I have on how to use how an MLflow project looks like. So this is like from a very old version of MLflow, but bear in mind. So this is like using like a Conda version. So this is how and this project is on GitHub. You can take a look at it. So you just specify the name, the Conda environment, and the entry points of your project. And then you obviously have a Conda file. It's basically like referring what are your dependencies, and like and on this case, Anaconda, sorry, Python, scikit-learn, the version of Python, MLflow version as well, and another like library that I used on this toy project. So this is like a very simple project that shows how it works like how do you integrate your training process in MLflow. So you just add this with MLflow start run. So it will assume that like it'll be able to hold and run all the metrics that you're interested on. So you have the training data component, like imagine this is like super abstracted here. So you prepare your data and you do a couple of other manipulations of your data, you train, and you just run a classifier here and you predict. So what you can do here magically is log your model, like so this version of your model, and log some metrics as well. The pretty thing, just with this piece of code, you now have like a deployable model. You can run an API directly on the model, and obviously you can have access to a UI that like logged your experiments. For instance, like the way that you run, you can just like on like from ML like on the root of your directory, you just do ML for run, and it will run, or you can run directly from GitHub. That's for me one of the coolest features. So it enhances reproducibility. So you can run directly the entry point dimension. So this is how like the UI looks like. So these are like different like model runs, and these are like some machine learning metrics: one score, precision, and recall. And you can compare the multiple versions of these metrics as well. And this is how a run is saved in MLflow. You have the command, you have the git commit, the run ID. So we're starting to like mix up with software engineering good practice. And you have the metrics. And the artifact is also saved in here in a pickled model. Your model is pickled. So this is like saved, and you can reuse and distribute as well. And automatically you can just run it as an you can serve it in curl directly now. You have access to a small API that can empower your POC immediately. Cool. And yeah, and like giving more context on MLflow. So like when else, like you log your models, and you can also load, because you actually load your models from there. You can there's a model registry in MLflow that you can use, similar to what the Cassandra store that Uber uses in Michelangelo. So like bits and pieces, you can, with mixing up with other tools, actually like have like a pretty good architecture using MLflow. This is what like a prediction monitoring dashboard might look like. This is kind of a heat map of features, and you can do like interesting things around like the distributions and predictions as well. And this is like monitoring dashboards. And this is around the divergence between training data and the data that you're actually receiving. So your model was trained in a distribution. So the distribution that you receive for inference can be that different. So this is like a representation of this distribution of the features. Another cool tool that we have also like evaluated is SageMaker to implement the continuous release for machine learning. SageMaker and the deployment and AWS Cloud Deploy as well. So you can actually do a lot of these things directly in SageMaker, and they already have like infrastructure to do inference and saving if you are in the AWS environment. But all the other tools are like kind of equivalent on the space, like if you use Kubeflow and things like that. So this is like an example of a SageMaker like cloud formation pipeline. So you can describe everything like your data bucket, the training process, your GitHub, like your GitHub repo that will trigger this pipeline, and like at the endpoints of your model. And the cool thing of SageMaker is that it has like pre-prepared like machine learning optimized training like instances. Cool, and this is how it looks like in AWS. So this is like your pipeline. So from the change in your source code, we train directly in your pipeline. We call SageMaker on your pipeline, and the output of training is on your deployment pipeline. But obviously, this requires manual intervention and things like that. So this is like the example of operating SageMaker. What I want to say is just like a few lines if you want to automate a couple of things. And this is, yeah, and you can have an approval gate to just like look at some metrics, for instance, like these metrics, and then just go here and do a manual approval of your model deployment. And yeah, and it's quite cool what like modern like tools can give you these days. Yeah, so this is basically the call, like the my talk, and like wrapping up. Basically, I'll say yeah. So yeah, 3 or 4 points. Like yeah, software engineering principles are very important. Looking at prior art in the industry is super important, but keeping up with developments on this industry is also very hard. So like, for instance, a tool like Kubeflow just became 1.0 recently, but changes are like, things are moving very fast. So keeping up with what's happening is very hard. But like, I think retaining a couple of principles that are relevant to your organization are a good approach to like conquer the world of machine learning engineering. Thanks. That's it.